So where we left off last class was just the portion that we didn't get to for section 7.4, which deals with sample sizes. So just like I said last class, what we're doing now with our sample size consideration is you can kind of think about it as we're working backwards, right? What we've always done so far is we've been given a confidence level, we've been given some kind of sample size, we've been given some kind of standard deviation and the mean. And we're saying, hey, using these things, figure out an interval that you have that level of confidence in. So we were always trying to get towards that interval. That was our final objective. But now what we're going to say is this. Suppose that you want to come up with an interval, and you want this interval to have a certain margin of error size, right? And you want to make sure that you're within that margin of error size, and you want to have a certain level of confidence in that. Well, the only thing that we would still need to know then is how big of a sample size do we have, right? For example, let's say that I said, hey, tell me what the average height is of of students at UNC Charlotte, but tell me your interval with at most 1 inch of margin of error, right? So now what I'm doing is I'm fixing that margin of error. I'm saying I don't want it to be any greater than an inch, right? And I want to have a certain level of confidence in that. Maybe I come up and I say, hey, tell me with 90% confidence the average height of students at UNC Charlotte to within 1 inch of what the actual amount is. Well, now the thing that you would need to know is you would have to say, hey, how big of a sample size do we need? So that's why we're kind of, like I said, you can kind of think about this as we're working the opposite way around, right? Instead of getting a sample size and then coming up with an interval that just has some random margin of error, we're fixing the margin of error and we're determining our sample size. Right. So here, another way of saying that is we're trying to determine the minimum sample size for some estimate of the population mean. So now we're going to go back to dealing with means, but we'll come back to proportions down here at the bottom, but we're just going to revisit the means here for a second. If we're trying to estimate what minimum sample size that we need, we're going to be using this formula right here. You can use the formula that we had before to solve for little n, and that's essentially what this is right here. So another way of saying that is in our margin of error, in our confidence interval formula, we had z sub alpha divided by 2, so we're already familiar with those are. Here we're going to be using sigma. We're not going to be using little s. We're going to assume the fact that we know sigma. And then here, what does E stand for again? Our margin of error, right? So we're going to fix the margin of error. They're going to tell us what the population standard deviation is right here, more specifically the population variance. And we're going to also have a certain level of confidence. From that, then it just becomes an arithmetic exercise to calculate out n. The most important thing here is that we always, always, always round up. Now, why does it make sense that we always have to round up? Suppose that I asked you, I said, hey, I want you to tell me the average height of all students at UNC Charlotte to within an inch. How many people do you need to go find out? Well, what we're going to practice now is we're going to put numbers into this formula. We're going to spit out an n. And what happens if that n that it spits out says 45.7? Right? So what that means is that you would have to go out and measure 45.7 people. Well, could you measure 45.7 people? No. So if that's your minimum threshold, you need to measure 46 people. So that's why we're always, always, always going to round up. Whatever our number comes out to be, we're always going to round up. Whether it's measuring people, measuring things that come off a factory production line, or what have you, we're always going to round up. That's the intuition behind rounding up. So let's do it. It's a minimum sample size for the population mean. An economist wishes to estimate with a 95% confidence interval the yearly income of welders to within $1,000. She estimates that the range of incomes is no more than $24,000. So using the empirical rule, she estimates that the population standard deviation to be about 1/6 as much, or $4,000. Find the estimated minimum sample size required. All right. So let's break this problem apart. First off, we want to determine how do we know that we're supposed to calculate out little n. Well, here it says find the estimated minimum sample size. And whenever it asks you to find the estimated minimum sample size, we're always going to try to solve for little n, right? Because our sample size is always little n. So this is what we're trying to figure out. We don't know this. We're trying to figure it out. Well, the next question that we're going to start to ask ourselves is, and this is just a foreshadow a little bit to when we get to proportions, is here, are we dealing with averages or proportions? And why is it average?
Isn't it because it's like it says she estimates population, standard deviation, and all that? Like you doesn't really say population proportion.
It doesn't say the word proportion. That's a very, very good indicator. But what are we talking about? We're dealing with an average. What average are we talking about? The average income, right? We're talking about average income here. So we're talking about an average income. We're not talking about the proportion of welders that earn above $100,000 or anything like that, right? We're not talking about proportions. We're talking about average, the average income. All right. So now that we know we need to calculate out the minimum sample size of something, and we know that that something is an average or a mean, now we know that we should be using this formula right here. So we have z sub alpha divided by 2 squared times sigma squared divided by e squared. And let's see if we can fill in these values. First thing that we want to know is what is our, well, any one of these symbols right here. What's our margin of error? Let's start in the denominator.
Our margin of error is 1,000.
1,000, right? And how did you get that?
Because it says the yearly income of welders 2 within 1,000.
Good. This within number right here, that's usually your telltale sign that whatever comes after that is your margin of error. So we know that our margin of error is 1,000, and we want to have our margin of error squared, so therefore we're going to have 1,000 squared. Everybody good with why that's 1,000? And whenever you look for the word within, like I just said, usually right after the word within, you can find your margin of error. That's a general rule. Obviously, it's not hard to pass. All right. Then we're looking for sigma squared. What do we have as sigma squared?
4,000.
4,000, right? So here it says that our population standard deviation to be about 1/6, or about 4,000. So we know that our population standard deviation is 4,000. Do we have to square this?
Yes.
Yes, we do, because here sigma is our population standard deviation. We want to have our population variance, or sigma squared, so we still have to square that. Everybody good with why we're squaring 4,000? All right. Then the last thing that we want to know is z sub alpha divided by 2. How do we figure out what z sub alpha divided by 2 is? Awesome. Same thing that we've been doing all along now, right? We have 95%. We're trying to calculate out 95% confidence interval, so we have a 95% confidence level. So therefore, how big is alpha? 0.05 or 5%. Alpha divided by 2 then is? Good. 2.5% or 0.025. And the z value that corresponds to that is?
1.96.
Everybody good with 1.96? Any questions about how to get 1.96? Right, and then we're going to square that. And here we have it. It's just plugging in those values. Any questions about how to identify any of those values? I'll spare you guys the arithmetic. Comes out to 61.47.
I do have one question.
Yes?
So the problem, if it says, so it's like within 1,000,
Yep.
why not go into put 4,000 and not 1/6 for your standard deviation?
Yes.
Okay.
So this portion right here, she's estimating the range of incomes to be no more than 24,000. So using the empirical rule, she's estimating this to be about 1/6. I'm just going to stop right there, right? Suppose that we didn't get this other portion right here that I'll now underline with a squiggly line, right? Exactly. So now it'll be 1/6 of 24,000, and 1/6 of 24,000, or 24,000 divided by 6 is just 4,000. So what they're doing right here with this empirical rule is Um, what do we know about the empirical rule? What were those three values I said you guys should remember for the empirical rule?
99, 68, and 95.
68, 95,
And
99.7. Cool. So those are the three values, 68, 95, 99.7. One standard deviation on each side is 68, 2 is 95, and 3 is 99.7, right? So if you go 3 standard deviations of the mean, what you're doing is you're taking that section, right? So you're taking that section. Let me draw a picture. If you go 3 standard deviations of the mean, so 1, 2, 3, 1, 2, 3. From here to here, you're dividing that up into 6 sections, right? So here you got 1, 2, 3, 4, 5, 6. Right, so everybody good with that? So what you're saying then is that if you go 3 standard deviations this way and 3 standard deviations this way, we know that 99.7% of all values, which is pretty much all values, are within this 6-section area. So therefore, here we know that each one of these sections is how big? 4,000, which is just 1 standard deviation. Right? So therefore, here we have 1 standard deviation, 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 1 standard deviation. So if we can take our range of values, which is 24,000, so we're saying that, hey, here we're going to have 24,000. Then one of the things that we can do to figure out the approximate size of a standard deviation is to take 24,000 and divide it by 6. That's going to give us an approximate value. Now, is it going to be exactly 4,000? Why not?
Because it's like about, and like once, I know the answer, it's just not going to come out now.
Okay. So here, we're saying that our total number that we're going to have between these two cutoffs is 24,000. But the empirical rule says how much is in this area? 99.7%, right? So what we're doing is we're taking our entire range and we're shoving it into the area where there should only be 99.7% of that range. Right? Is everybody good with that? So technically, we should have a tiny little bit of this 24,000 hanging over on this side and a tiny little bit of 24,000 hanging over on that side. So therefore, our standard deviation should be, oh gosh, is it going to be a little bit less? It's going to be a little bit greater than, a little bit less than 4,000. All right, anyways. That's besides the point. This is one of the more difficult questions that I've seen on past common finals before. So that's why I put it in the notes instead of giving it to you guys as a homework or a test. Obviously, you don't really need to know all this empirical rule stuff since they spit out the number for you right here. As long as you can identify these 3 values for this formula, you should be good to go to find the minimum sample size. All right. Are we done with number 1? Why not? Got to round up. So we don't want to know the income of 61.47 welders. We're always going to round up. So we're going to have little n is equal to 62, which is our final answer. All right. How do you guys feel about number 1? Make sense? Right? All right. What we're going to do at number 2, or I guess I call this a number 1 as well. Whoops. It's kind of like a different section. Maybe we're starting over the numbering system. Anyways, what we're simply going to do in this section right here is we're just going to deal with the population proportion. The only thing that we're going to be doing differently here is instead of having sigma squared up in our denominator, up in our numerator, we're going to have p hat times 1 minus p hat. So therefore, our problem needs to tell us what a sample proportion is instead of the population standard deviation. But here's one important consideration. This is something that a lot of times trips people up. If you see some problem and they do not tell you what p hat is, there's a rule that we use where we're going to use our default for p hat as being 0.5. And what we're calling this default of p hat being equal to 0.5, we're calling that our most conservative estimate. Our most conservative estimate. So if they don't give us p hats, we have to plug something in for p hat. So we're going to use our most conservative estimate for p hat, which is just equal to 0.5. Another way of thinking about that here is this, and this is a little bit mathematical aside. If you have two numbers, and these two numbers have to add up to 1, and you're going to multiply these two numbers together, which two numbers are going to give you the largest possible value? So you have two numbers. Call these two numbers A and B. A and B have to add to 1. And you're going to then take A and B, and you're going to multiply them together. What does A and B have to be in order for that product to be as large as it can get? What is it? So A and B have to add to 1, and A times B, you want it to be as large as possible. Yep. So if these two things is true, the values of A and B have to be 0.5 and 0.5. Right? Does that make sense? Let's say it wasn't 0.5 and 0.5. Let's say A was 0.1 and B is 0.9. Those two things add up to 1. What does this come out to be? 0.09. Right? Let's say that you make this a little bit bigger, 0.2, and then what does B have to be? 0.8. What do these two things come out to be? Definitely bigger than it was before. You could keep going on, right, and make this 0.3 and 0.7, 0.4 and 0.6, and you're going to see that it's going to keep increasing all the way until we get to 0.5 and 0.5, and then once we go past 0.5 and 0.5, it's going to start to decrease again. So therefore, our largest possible value is 0.5 and 0.5, which is just right in between, right? So therefore, what we're saying that if you now look back to this equation, if you want to come up with the most conservative estimate for how many people you're going to need to have in your survey, right? If I say, hey, tell me how many people you need to have in your survey to tell me what the average height is of all students at UNC Charlotte to within 1 inch. If you are too low, well, now you're not going to be able to give me my result. So you're going to go conservatively, and you're going to say, hey, I don't know, maybe 5,000 people, right? So a large number is conservative. Well, how do we make this thing right here large? Well, the larger that this portion right here is, the larger this is going to be. Right? Does that make sense? So how do we get this thing to be as large as possible? We want P hat and 1 minus P hat to be as large as possible. Well, how do we get that to be as large as possible? It's only going to be the case if P hat is equal to 0.5. And the only way, and the reason why we get P hat to be equal to 0.5 is from this thing that we just got right over here. So that's why P hat being equal to 0.5 is what we call our most conservative estimate. Everybody good with that? If all of that doesn't make any sense to you, don't worry about it. The only thing that you really need to remember is this. If they don't give you P hat, you use 0.5 for P hat. Cool? All right, so let's do it. It's another minimum sample size for population proportion example. It says find the necessary minimum sample size to construct a 98% confidence interval for P with a margin of error of E is equal to 0.05, assuming that no prior knowledge about P is available. All right. So, first off, let's try to figure out why we're going to be using one of these formulas. Here we're trying to figure out the minimum sample size. And again, that is our buzzword for trying to find little n. Everybody good with that? So it's like our first step. So our buzzword for why we're solving for little n is that it's asking us to find the minimum sample size. The second question we're going to ask ourselves is, are we dealing with an average here, or are we dealing with a proportion? Proportion. So here it says trying to find a confidence interval for P. And what does P stand for again? The population proportion. Good. So here then we're going to have Z sub alpha divided by 2 squared times P hat times 1 minus P hat. I don't know why I have this other one over here. Divided by E squared. So let's try to fill in this formula. Let's just start off with our Z value. Here we have a Z sub alpha divided by 2. How big is alpha in this problem? 0.02 or 2%. How big is alpha? 0.01 or 1%. And what's a Z value that corresponds to 1%? 2.326. Awesome. Is everybody good with how to get 2.326? Any questions whatsoever about how to get 2.326? Any questions? Anybody want to go over it? Still no takers? All right. So then, what is P hat in this problem?
0.5.
And why is it 0.5?
Because we don't have it given to us, so we use another conservation estimate.
Good. We do not know an estimate for P, so therefore we're going to use our most conservative estimate, and then we're going to use 0.5 for P hat, so then we'll have 0.5. I don't know why I keep making this other parenthesis over here. 0.5 times 1 minus 0.5. And what about E? What's our margin of error? E? And how'd you get that? It's like literally right there, right? Doesn't get much easier than that, so therefore we're going to square it since it's only telling us. Everybody good with these values in this formula? Because at this point, then it's just arithmetic, and if you do this arithmetic, you get 541.03. Is that our final answer?
No.
What's our final answer? 542. Good. Why is it 542? Good. We always, 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 always round up. No matter what the decimal place. Everybody good with this? All right. Take a minute or so for yourself and see if you can do B by yourself. Does anybody need a little extra time? All right. So then here, again, we're trying to find the minimum sample size, so we know that it's n. We're still dealing with proportions, so we're still going to use the same formula. we still have the same confidence level, so we still have 2.326. Right, is everybody good with that? We still have the same margin of error E, so we still have this down here in the denominator. Everybody good with that one? Then what do we have different? The p hat, so we know that here we're going to plug in 0.1 for p hat, so 1 minus 0.1. Is everybody good with this? Now, if you do this arithmetic, you're going to end up with 194.77. And then what are we going to do with that answer? Round it up. So therefore, n is going to be equal to 195. Everybody good with this? Now, again, like I said before, and I'm going to just reiterate it one more time since this is going to be the last time I'm going to say it, probably ever for you guys. Again, here down here in part B, we use p hat to be 0.1, and then this is obviously 0.9, whereas up here we use 0.5 and 0.5. Like I said earlier, it should give us a higher n value, which it did up here for part A compared to part B, and that's again why it's called the most conservative estimate, right? Because it's like, hey, estimate how many people need to be in your sample size. Your most conservative estimate would be to use 0.5, which obviously yields in a higher sample size. All right. Any questions whatsoever about this section or anything else for Chapter 7? All good? All right. Then that is Chapter 7.